fine. So we saved some of the best for the last. So we have a sequence of 2 talks by Aaron Roth from UPenn, and after Aaron, Vasilis from Microsoft Research. So it's a pleasure to have Aaron with us. So Aaron, take it away.
All right, well, thanks for having me. So I want to talk about sort of a very simple framework that makes it easy to derive all sorts of online learning algorithms that I think is cool. So let me tell you about it. So this is joint work with an undergraduate at Penn, Daniel Lee, and a PhD student, George Norav, and Malesh Pai. And so I want to start with 2 motivating problems, just sort of 2 cool examples of online adversarial problems, but these are sort of 2 examples of what are, many things that you can derive in this framework. But let me, walk you through 2 of them so that you have something concrete to hold on to. And the first is about predicting with sort of meaningful estimates of uncertainty. So think about what do or what should reported uncertainty estimates mean. And imagine that maybe there was a pandemic recently, it's just starting, it's moving through a population. And so it's an online problem where things are rapidly changing, like maybe the population of people affected is changing over time, the treatments are changing over time. And we need to make some kind of prediction as people come in, like given your features X that I can read off of your medical chart, what's your expected disease severity in 2 days' time? So maybe we've got some model for doing this, and then the doctor says, okay, well, given your features X, we think your expected disease severity is F of X. And so our patient might ask, well, how sure are you of this prediction? And the doctor could say, well, I've got a 95% prediction interval that your disease severity will be between, some lower bound L of X and some upper bound U of X. And so if the doctor says that to the patient, what does that mean? And so, the patient might ask, is this really a prediction about me personally? Like, you're stating this probabilistic guarantee. Is it a statement about what will happen to me 95% of the time, I guess, over the, unrealized randomness of the world? And if pressed, the doctor will have to say, no, that's not what it means. That would be impossible that would be an impossible prediction to make. What I mean is that this is a 95% marginal prediction interval, which means it's an average over people. What it means is that for 95% of people for whom with whom I have this conversation, the interval I give covers their label, and for 5% of people, it doesn't. And our patient might feel that this is unsatisfactory, for example, if she is part of a demographic group representing less than 5% of the population, because consistent with the promise of a 95% prediction interval, if it's a marginal prediction interval, is the possibility that it is always wrong for her and for people like her. It's just an average over this large heterogeneous population. There might be medically relevant demographic groups in this population that are just not captured in this model at all. So maybe it's more accurate for some people and less accurate for others. And so she could say, well, what about for people like me? And maybe, maybe different studies have been run. And so the doctor could, look up some medical studies and say, well, okay, for African Americans under the age of 50, the 95% prediction interval is from A to B. And for women with a family history of diabetes, the 95% prediction interval is from C to D. And for people with egg allergies and no history of smoking, the 95% prediction interval is from E to F. And note that these are not disjoint groups. So it could be that our patient is a member of all of these groups, and consistent with the guarantees of a 95% marginal prediction interval might be that, for example, A to B is entirely disjoint from E to F. So it's not at all clear how to interpret things like this. Okay, so that was marginal guarantees for prediction intervals. Perhaps you've heard of calibration, which is a marginal guarantee for estimating the mean. Right, so suppose I'm a weather forecaster and I make confident assertions like tomorrow there's a 30% chance of rain. Well, like, what does that mean? Tomorrow only happens once. And it's impossible to really check whether I was right about tomorrow in isolation or not. And so calibration is sort of this simple sanity check that marginalizes over days. It says, well, if I average over all of the days for which you predicted a 30% chance of rain, then it should average out to, it should, in the long run, have rained about 30% of the time. Similarly, if I average over all of the days for which you predict a 70% chance of rain. And maybe that's fine for weather, but again, if the promise is just, like for 30% of people for whom I predict they will need an ICU in 3 days' time, 30% of them really do, that is unsatisfying for the same reason that these marginal prediction intervals were unsatisfying, because it's averaging over what might be a very heterogeneous population that have medically relevant properties. And so Hebert Johnson, Kim, Reingold, and Rothblum proposed back in 2018 in a very nice paper, a really nice partial mitigation to this problem called multicalibration. They talked about it in the batch setting. I'm going to give you the definition for the online setting that we worked out in ITCS, but like the sort of the same thing. And the idea is very simple and natural in hindsight. It says, well, suppose I've got demographic groups, G. These are just subsets of the population. And so now, like, imagine people have features. They walk into my hospital, they present with features X, and well, they're a member of some of these groups and not others. The groups are just subsets of the feature space. Okay, these can be intersecting groups, so I might be a member of 5 of these groups. And what multicalibration asks for is that the sequence of predictions should be calibrated, not just overall, right? So when I say, 30%, so when I average over all of the days in which I say 30%, the average of the label should also be 30%. This should be the case not just overall, but also when I zoom in on each of the subsequences that correspond to days in which someone from each demographic group walked in. Okay, and so the nice thing is, you're making only one prediction per person, right? Like, you say, well, for you, there's a 20% chance of whatever event I'm predicting. And I might be a member of a bunch of these groups. I might be, Jewish, a professor, a resident of Pennsylvania, and I can interpret at my option this prediction that's been made as an average over any of those groups, and that average is correct. Okay, so that's a nice idea. And when you see that idea, you can generalize it to all sorts of other kinds of predictions, not just predicting means. So for example, I could say, well, I didn't like the marginal property of these prediction intervals. Maybe what I'd be happier with if I had some large collection of intersecting demographic groups is what we call prediction interval multivalidity. It's the natural extension of multicalibration to prediction intervals. And it says a sequence of prediction intervals is multivalid if, when I look at my empirical coverage probability, well, of course, overall, it should be 95%, but it should also be 95% when I zoom in on each of these different demographic subgroups, when I zoom in on the subsequence of days on which the person who showed up was in one of these different demographic subgroups. Okay, and this is, we want this to be the case even when the groups can be intersecting. So again, this sort of solves the interpretation problem. I might be a member of 10 of these groups, but you've only predicted a single prediction interval for me. And I can interpret this as a marginal prediction interval over any of the groups I am a member of, and the interpretation is simultaneously correct for all of them. Okay, so this is some problem. I think it's an interesting problem. Here's another problem. This was one studied by Blum and Licouris a couple of years ago that I'll call multi-group optimal assignment. Okay, so imagine I've got a sequence of people who are coming in, and I need to assign them to a judge who's going to make some impactful decision about them. Okay, so I've got this line of people. The first one walks in. I say, okay, you're assigned to the first judge. And the second one walks in. I say, you're assigned to the second judge. Okay. So in more detail, we've got individuals, again, who have features, and they arrive in sequence, and we've got a collection of groups. Okay, and an individual can be a member of more than one of these groups, and these groups can be arbitrarily intersecting. Well, as they arrive, we need to make assignments of these individuals to judges, okay, experts, if you like, who are going to make some impactful prediction. Maybe they're going to predict a label. So the jth judge will predict a label for the tth individual, y hat jt. And then, after we do this, we'll learn what the individual's true label was, and each judge will have made a mistake or not. Now, there's a bunch of judges, and the judges might have different error rates on these different demographic groups. Maybe some of the judges are better at making decisions for some groups than others. And so we can talk about the error rate of a judge on a particular demographic group. It is just the number of mistakes that that judge would have made on people from that demographic group had you assigned all of the people from that demographic group to Judge J. Okay, and the goal here is to assign people to judges so that up to diminishing regret terms, if I look at the average error on each group G, it would be as low as if we had assigned everyone from that group G to the judge who, in hindsight, had the lowest error for that group. Okay, so it's a no regret guarantee. It says we want to have no regret on each of these groups. But again, it's sort of strengthening sort of the standard no regret guarantee, which is a marginal guarantee, to one that's group wise. So not only do I want to have no regret on the whole sequence, but when I zoom in on the subsequence corresponding to people who are members of some group G, I want to have no regret on that subsequence to the best judge for that group. So on different subsequences, the best judge is different. And again, this is the reason why you can't just do something totally trivial like running a separate copy of multiplicative weights, say, for each demographic group, is that these groups are intersecting, they're not disjoint. So I might be a member of 5 different groups, and yet, nevertheless, when I want that people in Pennsylvania should be, should have prediction error as low as the judge, as if they had all been assigned to the judge that is best for people from Pennsylvania. But also I want professors to have error that is as low as if all judges had been assigned to, if all professors had been assigned to the judge who had the lowest error rate on professors, and so on. Okay, so it's taking a marginal guarantee like regret and sort of asking for this finer grained group-wise thing, just as multicalibration is asking for this finer grained guarantee with a calibration desiderata. And these are just 2 problems. There's lots of problems you can derive, and the solutions to lots of problems you can derive in the framework I'm going to tell you about. So for example, just about any notion of regret for a finite expert problem you've ever heard of: external regret, internal regret, adaptive regret, sleeping expert, subsequence regret. There's more whose names are escaping me. Basically, I haven't encountered one that doesn't fall out of this framework. Calibration problems, so I'll tell you about mean calibration, but we wrote a paper about calibration for variance. We have these prediction interval, multivalidity results. They all fall out of this framework. You can get a variant of Blackwell approachability from this framework for polytopes that has a fast convergence rate, and other stuff. So I'm not going to remind you what all of these things are, but I'm just going to tell you the framework and then give you some idea of how you can derive results for the problems I've told you about. Okay, so what is this framework? I don't know, by the way, if there's any way in this presentation format for anyone to ask me questions, but if there is, feel free to interrupt and ask me questions to the best of your ability. Okay, so what is this general framework? It's this quite simple problem that we call online minimax multi-objective optimization. So here's the idea. Play proceeds in rounds, and at every round, an adversary proposes a potentially totally new environment. So the environment you are playing in each round could be totally different. They don't have to be related to one another. But what's an environment? Well, an environment consists of some convex compact action set for the learner and some convex compact action set for the adversary, and a vector valued loss function that takes as input an action for the learner and an action for the adversary and spits out a vector, a d-dimensional vector of losses. And what we require is that if I look at each coordinate of this loss function in isolation, that coordinate should be convex in its first argument and concave in its second. Okay, so the adversary says, surprise, here's the game we're playing today. Could be different every day. And then after the learner sees the game, the learner selects an action. And then the adversary gets to look at the action the learner selected and select an action themselves in response. And this results in some d-dimensional loss vector. Now, these loss vectors accumulate over time. And what the learner wants to do is the learner wants to minimize the maximum coordinate in this accumulated loss vector. Okay, so there's these d losses. The learner cares about making the maximum of these d losses as they accumulate over time small. Okay. So this is the last day in a week of adversarial machine learning. So I don't have to remind anyone here what a zero-sum game is, but let me do it anyway. So a zero-sum game is defined by a minimization player who we will always associate with the learner. And the minimization player has some convex compact strategy space. And there's also a maximization player that will always identify with the adversary here, who also has a convex compact strategy space. And then we have a utility function that is one-dimensional, takes as input an action for the learner, an action for the adversary, and spits out a real number. And it's got to be convex in its first coordinate and concave in its second. And like the cool, like the one thing to know about zero-sum games is the Minimax theorem, which just says the order of play doesn't matter. Okay, so if the minimization player has to go first and announce their strategy, and then the maximization player has the advantage of getting to best respond to that with knowledge of the minimization player's strategy, or if in reverse, the maximization player is forced to go first and commit to an action, and the minimization player has the advantage of getting to know their opponent's action and best respond to minimize. At least if everyone's playing the game well, the outcome is the same. That's what the Minimax theorem says. Order of play doesn't matter. Okay. So, like we're playing some zero-sum game. We've got the thing we want to minimize is like the maximum coordinate of this loss function. You might think, well, maybe we can just define a zero-sum game where the payoff, the per round payoff, is just the maximum coordinate of this loss function, and maybe that works because we did assume that every coordinate of this loss function was convex concave. But that doesn't work, right? The max does not preserve concavity for the adversary, and it's not just like a technicality, like it really doesn't. So just to build some intuition, consider the following very simple game where the strategy space for the minimization player and for the maximization player is just like the polytope in d dimensions. So they both play some probability distribution over d things. And the vector valued payoff function, just in each of the d coordinates, is the difference between the probability that the maximization player puts on coordinate I and the probability that the minimization player puts on coordinate I. So it's just linear in each coordinate. So it's definitely convex concave. But note, if we care about the maximum of these coordinates, then if the maximization player is forced to go first and reveal his probability distribution, the minimization player can just match it and make sure that the entry in every coordinate is 0. So the max is 0. So if max goes first, min can obtain payoff 0, which is pretty good. On the other hand, if min is forced to go first and reveal her probability distribution, then max can just look at it and say, well, there's one coordinate on which min put weight at most 1 over d. Max can put all of his weight there and guarantee payoff 1 minus 1 over d. And here the payoffs are kind of like bounded by 1. So this is sort of like the worst gap possible between, the value of the game if min goes first and the value of the game if max goes first. So these really are different. Okay, so this is all to say, in these stage games, the Minimax theorem doesn't hold. So there are 2 values for the game. There's the value of the game when the learner moves first. Let's call that the learner moves first value. Okay, that's just the min-max value. So we're minimizing over actions of the learner, maximizing over actions of the adversary, and then we're taking the maximum over coordinates of this vector valued loss function. And then alternatively, there's the adversary moves first value of the game when the adversary is forced to move first. It is a disadvantage to go first, and so we know that the learner moves first value of the game is bigger than the adversary moves first value. And as we saw in an example, it can be strictly bigger by a lot. Okay. Now, of course, in reality, the learner moves first because we have to commit to a learning algorithm. And then we want to prove that it does something good against all possible adversaries. And so, in particular, like the adversary might be best responding to the choice of action of the learner every round. So we can't achieve in the stage game the adversary moves first value, but what we can still do is we can achieve diminishing regret to the adversary moves first value, even though the learner moves first. Okay, so we can't promise that in the stage game, but what we can promise is that if we look at the maximum coordinate of the accumulated loss functions, that the average of the maximum coordinate of the accumulated loss functions, this should be at most the average of the adversary moves first values of the game over time. These are different every round because the game could be totally different at each round, maybe plus some regret term that tends to 0. Okay, like it's possible we can do this, right? Because we get to average over time.
So Aaron?
Yes.
So it is, you're taking the max of the average here, right?
That's right.
And so somehow if you're taking the average of the max, then
that would be impossible.
That would be impossible by the last slide.
Exactly right. So the reason this is not impossible is because it's the max of the average rather than the average of the max.
Yeah. Okay. So is there actually intuition why the max of the average, this value that you're like, obviously you're going to show that you do pretty well here, but is there
like, why is this a reasonable
should be connected?
Like, are you asking why is this a reasonable benchmark, or
like why would it be that bad? I guess. It seems like the max of the average is very different than the average of the max.
It is, yeah. And in particular, the max of the average, we can like achieve this bound, and if we wanted the average of the max, it would be impossible. I think like a priori, like if you're just staring at this bound, there's no particular reason to think, like from first principles, maybe that this is the right benchmark. Like you might think maybe we can do better than this. I think the proof is sort of in the pudding, in that you can take this bound and then derive all of those other bounds for all of those other problems that sort of I listed on the slide. So this turns out to sort of be the right thing. And in particular, right, like one very simple thing you can derive from bounds like this is just the optimal. You can derive the multiplicative weights algorithm, which is sort of achieves the optimal bound for the very simple external regret problem. And we know that that is optimal, right? For many of the things we can derive, actually, like we know that the bounds are optimal, which sort of means you cannot improve on the generic bound. So I don't want to claim that it should be obvious that, like from staring at this, that deriving this is somehow interesting or the right thing. But what I claim is that, okay, this is something you can derive, and then from this, you can turn the crank and derive regret bounds for a whole bunch of other problems that turn out to be optimal.
Oh, thanks.
Yeah. Okay. So let me tell you briefly, like how you derive it, which is, like if you've worked a lot in no regret learning, like nothing here is going to be surprising. Like we're using reasonably straightforward techniques. Okay, so we're gonna move to a surrogate loss function. So remember, we care about the adversary moves first regret, and let's define the adversary moves first regret coordinate-wise. So we'll define the adversary moves first regret for the jth coordinate of our loss function. And this is just the sum over all of the time steps of the difference between the value accumulating in the jth coordinate of our loss function and the adversary moves first value of the game. And then the adversary moves first regret is just the maximum over all of these coordinate-wise regret functions. And right, and it's this maximum that's causing us trouble. It's the maximum that makes the game not convex concave. Okay, so a natural thing to do, and what we do is to swap out this max for a soft max. So our surrogate loss function will be this, will rather than being the max of all of these coordinate-wise regret terms, it's just the sum of the weighted exponential of these coordinate-wise regret terms. And the softmax is a very nice surrogate loss function, and it's upper bound. We can upper bound the adversary moves first regret, this thing we really care about, by the log of our surrogate loss divided by eta, our learning rate. Okay, another reasonably straightforward thing to derive about the surrogate loss function is that it telescopes, by which I mean the following thing. If I look at my surrogate loss today, I can upper bound that by some multiple of my surrogate loss yesterday, plus a weighted sum over all of the coordinates of my loss function of the increase in adversary moves first regret in that coordinate in isolation, somehow weighted by the total adversary moves first regret I've accumulated in that coordinate so far, weighted by the exponential. Okay, so my loss today, or after today, will be upper bounded by my loss yesterday, plus something that sort of looks like the sum over all of the coordinates of the loss function of my sort of per round increase in surrogate loss in that coordinate that's weighted by something that depends on how well I've done in each coordinate so far. And so a natural idea is to say, well, okay, I want to make sure that the loss doesn't increase too quickly, because in the end, my surrogate loss is going to upper bound my real loss. And the increase is really controlled by this sum here, the second term. And so maybe I'll define a surrogate game that I'm going to play in, a zero-sum game, that is just equal, where the utility function is just equal to this sort of second term here, the term that's going to bound my increase in surrogate loss. And note that in this surrogate game, what we have is a weighted sum of loss functions that are each convex concave rather than a maximum. And so like sums are nice. So a sum of convex concave loss functions is itself convex concave. And so this surrogate game is convex concave, and the Minimax theorem applies. Okay, so this is our surrogate game. And note that it's very easy to derive that the value of this surrogate game is 0, because the min-max theorem applies. So when we're analyzing the value of the surrogate game, we can pretend that the adversary moves first, because the min-max theorem says the value of the game is the same, whether the adversary or the learner move first. And well, if the adversary moves first, then by definition, we can achieve the adversary moves first value of the game. Right? That was the definition of the adversary moves first value of the game. And so we can guarantee that in every coordinate, our loss is less than the adversary moves first value of the game. And so the value of the surrogate game cannot be more than 0. Okay. Right. So we're taking advantage of the fact that we've moved to a convex concave game so that we can swap the min and the max and achieve the adversary moves first value of the game. Okay. And then the algorithm is easy, right? The algorithm is just write down the surrogate game every round, play the min-max equilibrium strategy of this game. That guarantees that the value of that game is 0, so that guarantees that when we're keeping track of the increase in surrogate loss over time, this term is entirely zeroed out, okay? And so the increase is very small. And you can, from that, relatively directly derive our final bound for the general framework, which is that when I look at the maximum coordinate of the accumulated loss vector, it's at most the average of the adversary moves first values of the games we've encountered plus optimal square root log d over t regret term.
So Aaron, sorry,
Yes.
can I ask? So you're saying that your surrogate game at each time step, the environment, sort of surrogate environment, this game is zero sum.
That's right. Like in the actual interaction, there's this like d-dimensional loss vector, but this surrogate game here, this is a zero-sum game with a maximization player and a who's the adversary, and a minimization player that's you, the learner.
And so how does this how does it correspond to you also want this I believe you. It's just confusing that this also then is a good approximation to the game that you actually wanted to play.
Well, the connection is that the game that I actually want to play has regret that is upper bounded by the surrogate loss. And the zero sum.
That is over the entire sequence of time steps, right?
That's right.
Okay.
And
good.
the stage game upper bounds the increase in surrogate loss per round. Does that make sense?
Yeah. Thank you.
Cool. Okay, so you get this regret bound. Okay, so let's turn the crank a few times. So from this, let's get multicalibration. So we need to define an action space for the learner and the adversary. Now remember, in this framework, we need the loss function in every coordinate to be like convex concave. And for some for some things like multicalibration, when you write down the obvious loss function, it's not convex, say, in the actions available to the learner. But there's like a simple trick to solve this problem, which is just to discretize the actions of the learner and define the learner's action space to be distributions, probability distributions over this finite set of pure strategies, which convexifies the problem. So we're doing that here. There's some discretization parameter controlling the how fine-grained the learner's action space is, and we're going to allow the learner to randomize. And then we'll say, okay, we've got to define a d-dimensional loss function that's going to be related. If we can minimize the maximum coordinate, will mean that we're multi-calibrated. So we'll just say, okay, we'll have a loss function that's going to have a coordinate for each group, and for each discrete prediction we can make, and for each direction, +1 or -1, in which our prediction might be either too big or too small. Okay, and if I predict P and the true label is Y, then in this coordinate of the loss function, well, it'll just be 0 if the person who showed up today wasn't in that group, doesn't contribute to loss for that group. It'll also just be 0 if I didn't predict P, doesn't contribute to the calibration loss associated with predicting P. And then it'll be either my prediction minus the label, or the label minus my prediction, depending on whether this sign is positive or negative. And note that if I can upper bound the maximum accumulated value of each of these coordinates, that will mean that I'm multi-calibrated. So we have to apply this framework. Upper bound the adversary moves first value of the game, which is pretty easy. Right? If the adversary moved first and told me a distribution over labels, then what I would want to do to zero out every coordinate is predict the mean of that label distribution. That would zero out all of these coordinates, and it would mean the adversary moves first value is 0. Well, I can't do that because like the adversary could play a distribution for which the mean was any real value, and my action space as the learner is discretized at multiples of 1 over r, but I can always play the closest multiple. So that means the adversary moves first value of the game at each round is 1 over r. Okay, because I can match the label distribution, the mean of the label distribution, up to the discretization error. And then I can just apply the general theorem and find that my multi-calibration error is at most, well, 1 over r. That's the adversary moves first value of the game, plus the regret term, which is just logarithmic in the number of coordinates. And how many coordinates are there? Well, just 1 for each discrete prediction I could make, 1 for each group, and 1 for each sign. It's just the log of all of that. Okay, and I can make r, like I choose r, right? So I can make r like a low order term if I want. It shows up only in the log. And just to like mention that this is not merely like an existential result, right? There's an easy way to turn the crank and to get the algorithm. And you can do that in this case and get quite an efficient algorithm. You just have to, right, with the algorithm is always play the min-max strategy of the surrogate game. And oftentimes when you just think about that, you can get it in closed form, and always you can get it by solving a linear program that has a number of variables equal to the number of strategies available to the learner, and a number of constraints equal to the dimension of the game. So I won't go through the algorithm, just to note that for everything you derive in this way, you can turn the crank, solve an equilibrium computation problem, and get an algorithm. Okay, how about this multi-group optimal assignment? Well,
Aaron,
same thing.
Can I ask one more question?
Yes.
Going back a slide, what is your calibration loss here? P you're thinking of as like in the simplex, or actually
so here P is one of the discrete
okay.
predictions, and I'm glossing over the issue of bucketing, which
great. Yeah,
you understand, but is difficult in a talk.
Great.
Yes.
Thanks.
Yes. Okay. So I've got a couple minutes left, so let's derive some more stuff. How about multi-group optimal assignment? Well, again, I'm just going to define a loss function that has a dimension for each group and for each judge. And well, like my action space as the learner in this problem is to choose a judge. And the adversary's action space is to choose a label for the person who showed up, as well as a prediction for all of these judges, which establishes, if they choose a distribution over such things, an error rate, an error probability for each of the judges. And so my loss for each group and for each judge J prime, well, it's just 0 if the person who showed up today was not in that group. Otherwise, it is just sort of my per round regret, right? I chose action J, I chose judge J. What is my regret to judge J prime? Well, it's just the indicator of whether judge J, the one I chose, made a mistake today, minus the indicator of whether judge J prime made a mistake. I have regret to judge J prime if my judge made a mistake and the other guy didn't. And again, if I can bound the accumulated, if I can bound the accumulated loss for each of these coordinates, that will mean that when I look at the regret for each group to the best judge in that group, it'll be small. Okay, and here the adversary moves first value is 0, right? The reason is once the adversary commits to a distribution over labels and predictions for the judges, that gives us sort of an expected error rate for each of the judges on this individual. And if the adversary told us ahead of time what the error rate was for each judge, I would just assign the judge to the, I would just assign today's individual to the judge that had the lowest error rate. That would sort of make all of these coordinates non-positive. And so again, we can invoke the generic bounds and find that simultaneously for every group G, if I look at the average error rate for people in that group, it is at most the average error rate for made by the best judge for people in that group, up to this regret term that scales with log of the number of judges times the number of groups. And once again, you can turn the crank and derive from this automatically an efficient algorithm for doing this. Okay, and then here's like a neat thing. You can combine multiple constraints. So say I want both multi-group regret and calibration, and say that I wasn't using the 0-1 loss function, but I was using a proper scoring rule as a loss function, something like squared error or log loss. Then fixing the adversary's distribution over labels, the prediction that minimizes loss is just the expected value of the label distribution, and so also satisfies calibration constraints. Which means that if I want regret constraints that are measured with respect to some proper scoring rule, this is compatible with calibration constraints. And so you can get Calibeating, which is a word that Foster and Hart came up with in a paper they put online last year. So here's a picture. Again, you've got these people showing up. And now you've got a bunch of different arbitrary models who are each making predictions about the labels that these people will have. You, the algorithm, sitting down here, look at these labels, and then you get to make your own prediction. Okay. And the goal is that, every day, right? So the model is, you've got these M models. Every day someone shows up. The models produce predictions. You somehow combine those and produce your own prediction and then learn the label. And the goal is not only should your predictions be multi-calibrated, but they should have lower squared error or lower error according to whatever proper scoring rule you care about compared to any of these models. And in fact, they ask for not just lower squared error, but strictly lower squared error to the extent that the models you're improving on are not already calibrated. And you can immediately get that result here as well, except with a better dependence on the number of models, by just combining the sort of coordinates that we put in our Minimax framework that come from the multi-group regret constraints together with the coordinates that come with the calibration constraints, and noting that because the scoring rule is proper, you can simultaneously make all of these small when the adversary moves first. Right, if you predict the mean of the label distribution, you zero out the regret constraints as well as the calibration constraints. And so what you can get is that when I look at, for any group, the squared error of our predictions on that group, it is at most the squared error of the best model on that group. In fact, even better than that, better by the calibration error of that model. Plus a regret term that scales with the number of models and the number of groups. And also simultaneously, your predictions are multi-calibrated. Okay, so I'm out of time. So let me just point out that you can turn this crank more times to derive a bunch of other stuff if you like no regret algorithms. None of this stuff is not like new, right? Like we're re-deriving bounds that are already known, but typically we get optimal bounds and efficient algorithms. And the nice thing is that they all come from turning the crank on this same little framework here. So thank you. There's two papers. The general framework is in this paper that's not quite online. There's an older version of it online, but it's going to be called Online Minimax Multi-Objective Optimization, Multi-Calibeating, and Other Applications. And the paper where we derive the online algorithms for prediction interval multivalidity, that was in ITCS this year. So thank you.
Well, thank you, Aaron, for the very interesting talk. So there's one question in the chat. I'm not sure if it's referring to mathematical, it's mathematical or in practice question, but the question is, how do you compute the mistake or error made by judge roughly in a general sense?
Yeah, so let's see. So I mean, in general, you'd have some arbitrary loss function, but like in the slides, I was just talking about 0-1 loss. So someone shows up, the judge gives a prediction, y hat, then you learn the true label of the person, y, and you say that they've made a mistake if y hat is not equal to y. Okay, so that's the answer in the mathematical model. If you're asking about actually applying this to like judges, you know, it depends a lot on the
delayed response, presumably.
That's right. So so in the model in which we work things out, you get the response right away after, or rather you get the response before you need to make the next prediction. Now, in general, you know, like I guess you can always get response that is sort of delayed by R rounds and have some term that, you know, some extra term in your regret that grows and somehow in proportion to R. I don't know of, this wasn't something we were thinking of, and so I don't know a general method for I don't know a method for dealing with delayed response here that is better than any other method for dealing with delayed response. It's just not something we're thinking about here.
Hey, Aaron, thanks for the great talk. One quick question. So this idea of Calibeating is new to me. Have you thought at all about how that relates to this work on omni predictions?
Let's see. So it's not really new to you because you do something very similar in the batch setting in your multi-calibration paper. The only difference is, okay, so I don't think Foster and Hart had read your paper, but they ask for it in the online setting. And then there's this notion of like how much you're supposed to improve on the predictors you're beating. And in your paper, you have an improvement that depends somehow on like how much you've like changed the predictor you started with. Like how it somehow depends on how much the multi-calibration updates change the original predictor. And Foster and Hart define multi-calibeating with what I think is sort of a cleaner measure, which is that you can talk about you can decompose, say, the squared error of the original predictors into a calibration error component and the rest of it. And they ask for beating, you know, when I'm evaluating how well we do on squared error, it's supposed to be better than each of the predictors by exactly their calibration error. So that's another difference. But otherwise, I think it's sort of more. It's like morally up to this, you know, technical difference in what's being asked for. It's like the online version of your no harm property.
Cool. Thanks.
All right. Well, thank you.
Thank you very much.